is Lee Blackmon, and I'm in the engineering technology program. And engineering technology is how to be a technician, and I focus on things that are electrical. So it's a kind of a career-oriented program instead of a transfer program. What that means is that you can come in and get out in 2 years, so just 4 semesters, 2 years, and then have a degree. It's an associate's degree, an AAS, Associate in Applied Science degree. And that's a piece of paper that you can use then to go to apply for jobs, and it will qualify you to get through job interviews and some of those automatic screening things that the computers do when you apply for jobs. So there's a lot of jobs that only require a 2-year degree to be a technician. So you can look for those jobs and get them. So being a technician, engineering technician, is a very broad subject area. There's a lot of different jobs, a lot of different companies you can work for. And actually, most people don't know about engineering technology until they come and talk to somebody like me, or somebody like Michael or Gabby, or one of the other advisors that has a feel for it. It's kind of a secret sort of a career. Unless you've got a family member or neighbor or friend that's in it, you probably don't know about it. Everybody knows about engineering, and so they think about engineering, but this is engineering technology. So this is actually a lot more interesting and fun and doable than the engineering degrees, which are usually 4 years or even masters beyond that. There's a lot less math in being a technician in my program, a lot less physics and other kinds of physical sciences. We do some math and some physics. Everything is math and physics to a certain extent, but we make it very friendly and doable. We don't get much farther than algebra in the math and just a little bit of trigonometry. And the fun part about this job is really trying to learn about how everything works. You're trying to understand concepts. How does that thing work? How does that machine work? What's the basic operating principle behind some sensor or some controller? But in engineering technology, there's a million different titles, a million different jobs people don't know about. So for example, let me show you a couple of words here on a PowerPoint. So I'm going to practice sharing my screen here. The thing about engineering technology is you are basically trying to do 4 different types of things. You're trying to create things, you can design things, you can test and calibrate things, sensors, systems, you're installing equipment. You may be troubleshooting something worked yesterday, but it doesn't work today. You're trying to figure out what's broken. In the installation, you may be installing something brand new that's never been put together before at this company, or different pieces that haven't been put together in that combination. Or you may be fixing a part and putting in a new part in place of an old one, either that doesn't work anymore, or you're trying to make the system better. So you're installing something that has more function to it or operates faster or more efficiently. The testing and calibrating, just about everything you can imagine, right, has to have some sort of test to it. Even just a simple example, if you ever have a little scale in your kitchen that you use to weigh food, if you put some food in a bowl and put it on the scale, you really don't care about the weight of the bowl. So you usually put an empty bowl on the scale, and then you hit a little button that kind of zeroes that out, so that when you put the food in the bowl, you're just measuring the amount of the food. That's an example of calibrating. Testing, we do all the time. New products, especially like at John Deere, for example, they'll design new combines. They have to test those before they start manufacturing them. So they need technicians to test those first ones. First, they have to build them, so they're actually creating them, and then they're going to test them. So there's a lot of different areas that you can go into with that type of work. In terms of the kinds of things that you're doing at a higher level, different level, there is, in my opinion, this is a lot of fun. You get a lot of technology that you can play with, a lot of toys, expensive toys. You'd like somebody else to pay for them. And then as a technician, you get to go in there and hook them together and get them to work and understand them. And that's really a lot of fun. A lot of our program is playing with toys or technology to learn the concepts and get some experience. The other thing is that we're trying to do as a technician is we're trying to solve problems. When you have a machine that's not working, or you want to build a new machine that hasn't been built before, you are solving problems. And I think that that's what you're getting paid for, is you're solving problems. So you're going to be a problem solver. But you're working with your hands. You still have to use your mind, because you're going to be doing a little bit of math and trying to understand the physics of how this machine works. But you are working with your hands. You're taking things apart, you're putting things together, you're testing things. So you're usually moving around a lot. You're not just stuck at a desk the whole time. You're walking around in a manufacturing plant. You're going from your office out to a machine, or to a storage or a supply room, and getting things and going back out to the machine. The other thing, just at a high level, is that there is good money to be made here. It's, again, very surprising. In this kind of a career, engineering technology, you're usually paid by the hour. There are exceptions where you can get paid as a salary. The hourly pay could be, when you very, very first start coming out of college, it could be, in the $18 or $19 range. But it will quickly move up. Just within a year or two, you could be making $22, $24, $25 an hour within just a year or two of work, just to get some experience. So if you translate that into a yearly salary, if you're making $20 an hour, that's roughly $40,000 a year. If you're making $25 an hour, that's roughly $50,000 a year. And it goes up from there. And that's without overtime. So usually these technician jobs will offer you a chance to work some extra hours during the week, more than the typical 40, and then they pay you time and a half for that. So it's very easy to make pretty good money in this job very quickly, really. So let's see here. The title, if you had to boil it down to just one word, is that you're a technician. You're not an engineer, you're a technician. You're probably working with engineers to test some of the designs that they're making. It's a 2-year degree, get in and out in 2 years. A good thing about this job is that every day is different, as opposed to, say, a manufacturing job where you're working production, you're working on assembly line, and everything you're doing is kind of the same thing every day. This is more, you've got different problems every day, every week. You're working on new things, you're fixing things that you didn't know they were going to fail all of a sudden. So every day is different. It gives you a lot of variety. You don't get bored very, very easily. And then the other thing is that this job field is growing. It's growing at a nice steady rate, somewhere 4%, 5% in that range. People are retiring. There's more technology all the time. Everybody knows that. There's more automation going on. All these things are job security for us technicians, because they need technicians to install it, to calibrate it, to test it, to figure it out, to make it better as time goes on. And so that's good work for technicians. Does anybody have a question at this point? Has anybody got something they want to make a comment about?
Impressed with the piece that you've talked about how much it is just really being able to get your hands dirty and getting to play with things that, one of the things that I quote you on a lot when I'm talking about your program and you're in class is the piece about that a lot of people who think they want to be engineers actually want to be engineer techs, because that's when you still get to break things and take them apart and put them back together again.
Excellent. Thank you. Thanks for pointing that out. Yeah, and I actually wanted to you're making me think of a quick story. I just had a student who switched from the hardcore straight engineering into my engineering technology program a few weeks ago. And he's, a smart guy. That's great. And he was doing okay in the classes. He was getting A's and B's. He was taking calculus and all this physics and chemistry and stuff, but he just wasn't enjoying it. It was too much in your head and not enough doing something with your hands. And so he switched, and now he's very happy with what we're doing, playing with toys, and it's much more approachable types of topics that we're studying and information we're learning. Let me go on here. Okay, so that was kind of the word stuff. Let me kind of end that show. Again, is there anything that comes to mind as a question or comment? Anything that I said that was not clear, or makes you think of a question that I didn't cover?
So one of the questions that I get asked a lot, with it being a kind of practically based is how is this different than training to be an electrician?
Excellent question. There's two kinds of answers. One is that electricians tend to be in a union. When I think of the word electrician, I'm thinking about people that are in a union. And to be in a union electrician, they have some very rigid rules for that require a lot of work hours in order to be, accepted in the union as a tradesperson. And so you have to kind of have a job for about 4 or 5 years before you can become an electrician. You are an electrician while you're doing that, so I don't want to knock that. But electricians in general, as stereotypes, they're usually running wire. They're usually connecting wire from one point to another. They might be running it through a conduit and bending the conduit and that sort of stuff. They might be hooking up, light switches, that sort of thing, or even connecting it to a motor. But the contrast to that is the engineering technician is usually into an awful lot of things where they get probably a little bit deeper into what is this device and how does it work, so that if it fails, I've got a feeling of how do I detect that it failed, and then how do I replace it. So the technician is doing more problem solving. They have to have more knowledge about how does something work, so they can figure out what's broken with it or how to improve it.
That helps a lot. Thank you.
Yeah, you're welcome. Thanks for the question. I would like to, the time is going quite quickly here, and I would like to play with a video that I put together that has some students involved with it. So I'm going to go back to screen sharing here, and I'm going to see how my luck goes with pulling up a video. And excellent. This is very cool to me. This is a project that some of my students worked on. This is a robot that climbs stairs. These students made this up, two people, Chayun and Dan. They designed the mechanical look of this, right? They had to figure that out, which is quite a difficult piece of work. Then they had to program it. This is not radio controlled or remote controlled. This is kind of a little artificial intelligence. There's a computer inside there, microcontroller, that's figuring out what to do and when to do it. There's a sensor in the front you can kind of see over here on the front right that's detecting whether there's a step that it sees. And this is really a beautiful design. This is what happens in the 4th semester, just before they graduate, where they're dangerous enough now they can start putting stuff together on their own and making their own designs. Really a lot of fun. So this thing would climb. This is in building 2 here at Blackhawk, and they tested this, put a lot of hours into it, and it would climb those steps all the way up. Here's an example of something else. This thing on the left is a inductive sensor. And when I have a piece of metal, I just grabbed a stapler and put in front of this inductive sensor, proximity sensor. When it gets near enough to that, then I've got that as an input. So this is a sensor going into a PLC. Then inside the PLC, I've got some code written that will interpret that input. And when something gets close to it that has metal to it, then it will turn on something. This could be a light in this case. It could be a motor. It could be conveyor belt, all sorts of things. But this is an example of how a technician needs to understand what is this sensor, how does it work, what's this PLC, how do I code inside here, how do I wire this up with the inputs and the outputs to kind of help the engineer get their design into a product. So I think this is really cool. Here I'm actually just using a screwdriver that had metal in it, was enough to trigger the sensor. This is actually, by the way, this is how traffic lights work. When you see the kind of cutout places in the street underneath where your car is, it's actually picking up metal, detecting where there's metal. Here's students that are working with an Arduino. Up here's an Arduino processor. They got an LCD screen and they got a joystick, and they're going to have to program this. That Arduino is a microcontroller. So here they're writing some C++ programming code to download in it. This is another student working on a different project, again with an Arduino based, but he is, actually, I'm going to stop this and have him describe it real quick. Hold on here. Whoops, sorry, clumsy fingers. There we go.
What I'm trying to do right now is take a measurement from a soil moisture sensor and print it to an LCD screen. That's about it. The components here, we've got a sensor that runs current through the soil, changes based off of moisture. It's a range of 2 to 5 volts. We've got power, ground, and an analog out, as well as a digital out, the set point of which can be changed with this potentiometer. And then we've got our LCD screen with an I2C module on the back, which just reduces the number of connections we need to the Arduino board. So we've got serial clock, serial data, 5 volts and ground. Red cord's just to give some more ports.
So I'm going to stop him there. He said this is just the beginning of his project. So he's going to build a contraption here out of his mind to sense how much water is in a plant in his house. And he wants to find out when the soil gets too dry using this sensor. He wants this controller here, the brains, to be thinking. He's got a program that he's downloaded into this in C++ code again. And when he determines that the soil is too dry based on this sensor, what he wants to do is turn on a pump that would pump some water into the plant. So now the question is, how much water does he pump in there? And the cool thing that what he's going to plan to do is have some more sensors fed into here. These other sensors are things called strain gauges. Strain gauges are used to measure force. And so what he's planning to do, like I described earlier with the little scale in the kitchen, is he's going to build a scale under a bucket of water, essentially. And he's going to measure how much water he's putting into that plant by measuring the change in the weight of the water in that bucket, so that he can translate the weight of water to how much water he's putting into that pot. And that's a really cool idea. You're putting, again, all these things together in a new way and doing it yourself from scratch, along with some programming. So very cool stuff. Here is a principle of talking about magnetism and electricity. I love this also. This device up here measures current. It's just got a coil of wire here. And what I'm taking is a magnet and I'm moving it back and forth away from that coil of wire. And that's how you generate electricity. There's a magnetic field going back and forth across the wire, changing magnetic field in a wire. This is cool here. I'm going to stop this for a second. This is a 3-phase induction motor. This is a motor that was designed and developed by Tesla originally. He is the one who invented this. And the cool thing about this is that you're going to have magnetic fields that are pulling each other around in a circle. But usually, to get the magnetic field in the middle of the motor, you have to have wires going to it. Whenever you have wires going to something that's turning, you're going to have trouble. You're going to have some friction. You can have some wear and tear. And so it becomes a motor that requires a lot of maintenance. What Tesla invented was the idea that you can have a rotor here in the middle that can turn without any wires attached to it. And so to kind of show that and demonstrate that in this video, I've actually got the rotor removed from the middle of this motor, and I've got just a regular old pop can that's stuck through here, and this is just a string. It doesn't connect any electricity going through here, and it demonstrates Tesla's idea that rotating magnetic fields will generate electricity inside this metal, which in turn will generate its own magnetic field, and then you have magnetic fields pushing each other around in a circle. So, and then I do a little slow-mo here so you can actually see the rotation. But again, I think this is a really cool illustration of a concept. Technicians would be aware of this, whereas electricians wouldn't necessarily know about this. Here's a different lab we have in building 2, working on mechatronics, again with sensors and process control. This student here looks like he's generating some signals from the signal generator in the background. This yellow thing is a digital oscilloscope. He's going to look at the waveform. What he's got on this breadboard is an operational amplifier that he's going to amplify the signal. So a lot of times when you have sensors, the signal coming out of the sensor is too low to make it be seen by the next thing in line in the system. So you need to amplify that signal, and that's what he was doing, was making the signal bigger. This is a little bit of a view of some of the equipment that we have in the mechatronics. We have some pneumatics that deal with pressurized air. We've got some valves here we can open and close with pressurized air. All sorts of cool, again, circuits to build at Blackhawk College. Here's one of our students who is closely listening to a lecture here while I pester him with the video. This is a part of a thing called the Beast, which is a process control simulator in the back of the room. And here's a student who is working on a motor. You can see the other motor here to the left has the front taken off of it. Here's a student who's testing the motors. And if you see down in the lower left-hand corner, you can see sparks going on, those motors tested. This is a process control where we've got a level of fluid in a tank. We've got a controller here, we've got transducers, all sorts of stuff. One of the points of this process simulator is that it's very scary. Most students, when you first look at this, you're very scared. This is what you might see in a processing plant if you're making ethanol or if you're making chocolate or anything like that. And we teach them what these parts are and make them comfortable with this so that they're not scared and overwhelmed when they walk into a huge facility that's just stacked with this sort of equipment. I'm doing a lot of talking. Does anybody have a question or comment somewhere around here?
It all looks very cool, very fun.
Thank you so much for saying that. Oh, and I got to stop this for a second and let me start this over. This is a fun thing here. On the right is a signal generator. In the middle is a digital oscilloscope that's looking at a signal. So I'm generating a little bit of baby AC waveform that comes out of your wall, but just not that much voltage. Here we're looking at that sine wave. And then for fun, I've got speakers hooked up so that I can listen to that sine wave. So check this out real quick. My student's having a good time. She's playing with the frequency, and that changes the pitch. So music and electricity can go together. Here we've got a little robotic vehicle that's got whiskers on the front, and it's got some programming inside that the student put in there, and he's trying to avoid objects. So whenever the whisker hits something, it tries to back up and get away from that. Here's a different student that's working on getting his whiskers together. Here's a student that can't figure it out. This guy, I like him a lot. He was trying to, I'm going to pause this. He was trying to make sounds come out of his little robot vehicle. So there's a little round black thing here on top of this breadboard that's actually a speaker. And again, there's a processor in here, and he's got code that he's written back here on the computer and downloaded to it. And he was trying to make it sound like the theme song to a Mario Brothers video game. But he made a little bit of a mistake, and one of his wires that he connected up here, instead of it going to the speaker, went to one of the motors on the wheel. So now it's trying to play a song that's coming through as movement on this wheel, and it's actually a mistake. And so I'm giving him a hard time about it because it looks like that he programmed his robot to have a little stroke.
Dancing to the music.
Dancing to the music, that's what he's doing. But we have a laugh. We're always friendly and enjoying each other's company and learning as we go along while we play with all these toys. You can see he's laughing there. I'm going to stop this and see what this sounds like coming across to you guys. This is a student testimonial.
Yeah, different fields you can go into are, you can go into process control, you can go into system analysis. I mean, I know previous students who have come in here, they're working through John Deere and numerous different locations. There's somebody who is up at a chocolate factory up in Wisconsin, and it's opened so many doors to see what's truly out there in the world for the engineering technology field.
Again, he finally got his Bobot work in there, which is about backed off the table, and I had to swear at him a little bit. But now he's doing donuts. He's pretty happy. He owns that now. Here's another guy who was having trouble with one of his parts, and so he's having to readjust it. He had an LED that was stuck in the wrong way, so he had to put it in the correct way so it would work. So we're having a lot of fun here, programming and building and doing little robotics things. Again, here's doing some more testing. This is just a little pattern of going forward and then returning to where you started. Pretty proud. And then we're back to the beginning. All right, so let me see here. I'll stop sharing that. So I think that was the majority of what I wanted to talk about. Just a little bit about, a lot of it's visual, of playing with toys. It's electrical oriented, it's control, it's automation, it's sensors, figuring out how things work. We got solar panels, wind turbines. There's a lot of cool jobs that nobody knows about. For example, there's a product design and test facility, a couple of them in town for John Deere. And so when they build a new combine, when they design a new combine, they have to build 1 or 2 or 3 of them, and then they have to go test them. And so they will test them to make sure that they work properly. And then they will continue testing them to make sure that they don't fail too soon. So they'll do some accelerated design verification to make sure that would last 10 years or 20 years and not 2 days. All that kind of work involves technicians putting on sensors, then running the product through its paces, and then trying to take information from those sensors, calibrate it, turn it back into normal information like force and temperature, things like that, send that data to the engineers back at the desk that are working on that to make sure that the numbers make sense. The technicians, though, are having all the fun. Technicians have to travel. It's interesting, you can't test the combines inside a building and get all the information you need. So a lot of these people have to travel with the combines, and they'll go to Texas and California and Idaho and Canada. They'll go to South America, they'll go to Germany, they'll go to Australia. And I just think that's the coolest thing, to just go to school for a couple years and have this big company paying you to work with this high technology and travel all over the world and see the world on their dime. Very, very cool jobs like that. Robotics are also the same. In town here in the Quad Cities, there are 3 different national, if not internationally known robotics companies. In Bettendorf, there's a place called Vizient. In Davenport North, there's a place called Genesis Systems. It's not the hospital, it's a robotics company. And out in Milan by the casino, there's a place called Hawk Technology. All 3 of those companies are making large robotics equipment that are used in manufacturing at places like Caterpillar and John Deere, and they sell them around the world. And technicians have to go with them to make sure that they work wherever they get to. So an awful lot of jobs that nobody has ever heard of unless you come into this program and learn about it. Any other questions or comments? Because I'm thinking it's been about 30 minutes and that's a good time to kind of wrap up.
One quick question. I'm wondering what kind of student will be successful in this sort of program? It sounds like creativity is important. If you like hands-on, that's important. Do you need to be a math science type person too?
Not like you would typically think of a math science person. A lot of times when you're thinking of a math science person, they have to, they do all this calculus and this nuclear physics and stuff. And we're not at that level. We're taking it at the level where we're playing with things that have already been invented. We want to understand how they work so that we can predict how they behave. But we're not trying to really create new scientific discoveries so much as we are trying to assist engineers. So the more we know, the better, right? The more we know, we'll get more responsibility and more money. But there's a lot of varying degrees between that. So really for the math, it's algebra. So you need to not have a anger management issue with numbers. You need to be serious. You need to be okay with, multiplying and dividing and a little bit of algebra, going back and forth between decimals and fractions, that kind of a thing. And then the physics, to me, it's a beautiful curiosity. How do these motors work? What's the principle? Instead of just saying, oh, it's all magic, you go, oh, yeah, I understand how the electricity makes the magnetic fields, that sort of thing. And so you understand the operating principles, even the sensors. Yeah. Thanks for the question. Any other comments?
I think the other piece that I noticed just with all the videos that you showed us and that kind of thing is it's definitely not a program that's focused on sitting and staring at a board or listening to a lot of lecture. It's definitely a hands-on kind of learning experience. Not that you might not have a lecture here or there, but for people who really feel like that they learn and enjoy being hands-on, that it definitely serves to that group. So we definitely appreciate you sharing all the things that you have about the program. Thanks, Lee.
Great.